Section 23.3. The energy corresponding to the H2 plus molecular wave functions psi g and psi u. Psi g and psi u are the mathematical descriptions of the bonding and antibonding molecular orbitals in this H2 plus molecule. When you have a system that consists of three or more charges, such as H2 plus, it's impossible to solve its Schrödinger equation exactly. We cannot solve this. However, we can make approximations. One way is to propose a trial wave function and then use the quantum mechanical postulate 4 to calculate the trial energy. If your trial wave function is reasonable, then your trial energy is reasonable. If the trial function is already normalized, that means this integral is exactly 1. And then the trial energy is simply this integral, the product of two terms. This is the complex conjugate of the trial function. And this is the Hamiltonian operator being applied to the trial wave function. So now we propose two reasonable trial functions, psi sub g and psi sub u. Psi sub g is the constructive interference of the two 1s atomic orbitals, each centered at one hydrogen nucleus. Psi sub u is the destructive interference of the two 1s atomic orbitals. And over here, this is a normalization factor for psi g. This is the normalization factor for psi sub u. So this is normalized. This is also normalized. S sub AB is the overlap integral between this 1sa and 1sb. So this is the form of the overlap integral between the 1s atomic orbital centered on hydrogen A and the 1s atomic orbital centered on hydrogen B. When A and B are close, we have a larger integral. When A and B are far away from each other, we have a smaller overlap integral. Now both psi sub g and psi sub u are normalized, and therefore we can easily calculate the trial energy of the bonding orbital and the anti-bonding orbital. This is the trial energy of the bonding orbital. So you just need to plug in this complex conjugate of psi. In this case, it's itself, because this wave function is a real function. And then you need to apply h to the wave function. We can take this out of the integral, this out of the integral. So we have this here. And then we need to evaluate this, right? Without doing any detailed mathematical derivation, I'm going to say this integral is equal to HAA plus HAB plus HBA plus HBB. H sub AA is simply the integral of this 1sa wave function times H, the Hamiltonian, being applied to the 1sa orbital. And then you have HAB, you have HBA, and then you have HBB. Because of the symmetry in this H2 plus homonuclear diatomic molecule, we have HAA equals HBB. HAB equals HBA. So this molecule has a D infinity H symmetry. Or you can say H2 plus belongs to the D infinity H point group. So now we can express the trial energy of this psi g bonding orbital. So it's this. And again, HAA is equal to HBB. There's no difference between hydrogen A and hydrogen B. HAB is equal to HBA. So we got this formula, or this formula. Similarly, the trial energy of psi u anti-bonding orbital is HAA minus HAB divided by 1 minus SAB. So you replace this plus sign with a negative sign. This plus sign with a negative sign. What's the physical meaning of HAA? The 1s atomic orbital energy in the hydrogen atom is HAA. So really, HAA is negative 1/2 atomic unit. In this case, the ionization energy of the hydrogen atom is negative HAA. HAA, H sub AA is negative. So negative HAA is positive. The ionization energy of the hydrogen atom is positive 1/2 atomic unit. And I think it's roughly 1,322 kilojoule per mole. In the hydrogen 2 plus molecule, we have this bonding orbital energy, antibonding molecular orbital energy. So this bonding orbital energy is lower than the atomic orbital energy. This antibonding orbital energy is higher than the atomic orbital energy. We can also define the shift of the MO. All right, so Eg minus the atomic orbital energy is the shift for this bonding orbital. Over here, this is a shift for the antibonding orbital. Delta E sub G is always negative. Well, it's bonding orbital. Delta E sub U is positive. It's antibonding orbital. The bonding orbital lies below the atomic orbital. The antibonding orbital lies above the atomic orbital. It's possible to prove that this delta E sub G is less than delta E sub U in their magnitudes. So what does that mean? Well, that means if you have H2 2 minus, then you have 4 electrons. You have to put 2 electrons in this psi G orbital and 2 electrons in the psi U orbital. The electron decrease by putting 2 electrons in the psi G orbital is less significant than the energy increase by putting 2 electrons in the psi U orbital. So that means it's impossible to form this H2 with 2 minus charges. Now we have a molecular orbital diagram of H2 plus. So H2 plus can be formed by one hydrogen atom and one H plus. And over here, this is the 1s atomic orbital. So when they form psi G and psi U, psi G lies lower than the atomic orbital. Psi U lies above the atomic orbital. So this energy decrease is smaller than this energy increase. All right? And then you put 1 electron in the psi G orbital. You always put the electrons into the lower MOs first. What about the MO of H2? Well, you just need to change this H plus to H. Put an electron here, and then put an electron here. Now you have the molecular orbital diagram of H2. Now what about H2 minus? H2 minus means you have 3 electrons. So you can put 2 electrons here, 1 electron here. 2 electrons here and 1 electron here. This H2 minus does exist with a bond order of 1/2 because you have 2 bonding electrons and only 1 antibonding electron. H2 2 minus, you need to put 2 electrons here, 2 electrons here. 2 electrons occupy the psi G, 2 electrons occupy the psi U. But again, the energy increase is greater than the energy decrease. So it's impossible for 2 H minus ions to form a bond between each other.